biased review, I guess. But thanks very much for the invitation, and thanks to the PCMI program for constantly supporting this effort in trying to characterize the role of the H2 molecule and it's let's say it's an investigation of whether H2 is a reliable and quite unique tracer of the dissipation of mechanical energy in galaxies in general. So I will try to put this in the context of galaxy evolution. So I'm mostly interested in this role as a tracer of turbulence and mechanical energy dissipation in active phases of galaxy evolution, like AGN feedback or merging galaxies. So I'll try to go through those questions and points here. A very fast introduction about why H2 we think is a good tracer of those processes, essentially because it's an efficient gas coolant, and we will look at phases where you need to dissipate both the gravitational collapse energy or the feedback-driven energy. And we think H2 is a good tracer of that. Then we will move to the transition between the Spitzer era and the James Webb era, and I will try to show how James Webb opens new perspective in characterizing H2 line emission in galaxies. Focusing on a few examples and one recent paper we did with people at LPNS about how to use those H2 line emission to try to gather the radiative energy and mechanical energy budget in galaxies. So a little bit of context, you know that when galaxy forms, they exchange mass with their halos, basically, and this gravitational potential energy actually dominates the young phases of galaxy evolution. So this mechanical energy has to dissipate for the gas to cool and form stars. And you'll see that H2 is the natural coolant from let's say the warm neutral medium to the cold neutral medium where stars are forming. And this is key in this talk. We think that this part of this mechanical energy cascades down to small scales. So under this talk, there is this idea of this turbulent energy cascade from the large scale of input of energy to the very small scales where energy is dissipating. And H2 is a key there because at small scale, at the scale of viscous dissipation, H2 is actually a natural coolant. Just a quick reminder by H2, what is key is that H2 traced by those, I don't have the pointer here, but okay, you don't see any pointer. Okay. Well, anyway, you see on the left, the rotational diagram of H2. And you see that those pure rotational lines on the left, so V vibrational state equals 0, they trace gas, let's say, above 50K to a few thousand Ks. And you've got a number that I've listed here. I'm not being exhaustive here, but there's a couple of number of processes to excite and populate those levels, including collisional excitation, which is one of the dominant mechanisms when you go high up in energy, and obviously UV pumping. In standard star-forming galaxies, we see a very tight correlation between the infrared luminosity, the PAR luminosities, and the H2 luminosities, meaning that mostly the H2 is coming from PDR, it's coming from photo excitation, UV pumping. But the discovery with Spitzer and James Webb, you'll see, is that now we find a couple of galaxies where H2 is in excess of what can be accounted for by photoionization models. And on the right, thanks. Okay. And then, thanks very much. And on the right, you see those dominant rotational lines, so S0, S1, S2, S3 that I will be talking about, probed with James Webb. So with James Webb, we probe from the S1 line up to very high levels. And you see that is a natural coolant when you go from warm ionized gas to cold molecular gas traced by CO. So H2 is this natural coolant and path from the warm to the very cold medium traced by CO. So it's a very complementary tracer that traces the energetics, whereas CO traces the mass budget of the molecular gas. And on the other way around, I've put those arrows in both directions because let's say that you have cloud-cloud collisions, or you shock molecular gas where you go from the left to the right through H2 also. Okay, just very quickly, you see here a sensitivity plot of the James Webb instruments compared with previous generation of infrared telescopes, including Spitzer, and you see that you've got a 2 order of magnitude, or sometimes more in the near IR, 3 orders of magnitude compared to previous generation instruments. One quick example where we really see H2 as a dissipative agent of mechanical energy. The first example is protostellar outflows. I'm not gonna talk into details about that, but this is HH221, and this is a very famous NIRCam image where you've got a young protostars forming and you've got gas swept up by protostellar outflows. And basically on that image, it's a combination of filters. All of those filters, except maybe the last one, the 4-micron filters, which is dominated by the ladder of CO, all of the other filters, from the purple to the orange one, are dominated by H2. So here we've got a clear source of mechanical and radiative feedback. And when you look at the spectrum, it's actually a barcode of H2 with, as I was saying, CO, the R and P branch of CO. But you see all of those lines here are rotational or row vibrational lines of H2. So this is quite spectacular and a nice manifestation of this kinetic energy dissipation. With MIRI, we can probe the bulk of the warm H2 mass through those rotational lines. And now we've done maps. So this is a recent paper where we've done mass of we can probe the mass of the bulk of the H2. So we've got a MIRI map, a spectral map with MIRI, and we can probe the temperature of the warm and colder component as probed with the rotational excitation diagrams of H2. And we see evidence of bow shocks. So you've seen temperature increases moving away from the source, so the temperature is increasing as you move away, which is a nice evidence of kinetic energy dissipation through shocks. Okay, I'm not going to enter into those details, but this is, I think, a clear example where we can learn the physics of this energy dissipation, where we can resolve things. Now, James Webb is opening a new era where we can actually spatially resolve at giant molecular cloud scales, a few parsec in nearby galaxies, or even a bit less in some nearby galaxies. And the point is that, well, talking about bubbles, Nicolas, we see bubbles everywhere. And the question we would like to address with spectroscopy is how and where is this energy dissipating? And this is very important to understand galaxy evolution. Actually, this is one of the key questions that can constrain feedback models of galaxies. There are a couple of very nice papers from the FANGS survey. So this is a James Webb survey of nearby galaxies, actually where people start to do probability distribution functions of the diffuse and clumpy gas on those galaxies. And they are actually confirming that those PDFs of densities and temperatures, they actually match simulations of isothermal turbulence. With Mach numbers between 5 and 15 in that paper. So we are starting to actually, the studies we were able to do in our own Milky Way, we can do it in external galaxies now. And the question is where and how is this energy dissipating? From the Spitzer spectroscopy, we found that we found a population of very bright galaxy in H2 line emission. So this is a plot where I've put the first rotational lines of H2 line emission, total intensity of H2 divided by the PAR emission, which is a nice tracer of the UV photoionization as a function of the infrared luminosity, the 24 micron continuum. And you see that standard star-forming galaxies, which are those black diamonds here, they lie onto this line, meaning that you've got a quite very tight correlation between H2 and pi emission, as I was saying, coming from PDRs. And all of those galaxies that are above that line, and especially above that dashed line here, are galaxies in the parameter space where we cannot account for the H2 through PDR models. We need extra heating mechanisms like shocks or turbulent energy dissipation or cosmic ray heating. And those population of galaxies, they are very diverse. You've got AGN from the early Spitzer days. The blue points here are nearby AGNs, and we were already seeing that those AGN depart from standard star-forming galaxies. And now we've got many, many galaxies, including bright cluster galaxies. So very bright galaxies in the center of clusters where you've got smoking guns of feedback, AGN feedback, for instance. So now with James Webb, compared to Spitzer, this is one example. This is Centaurus-A. So a study where we got nearly time to actually map the central part of the Centaurus-A, very famous radio galaxy. And you see the spectrum is basically dominated by H2. So this is very spectacular. And compared with Spitzer, which is this dotted spectrum here, now we've got the spectral resolution also to study the kinematics of the warm H2. With Spitzer, we had, you see on that line here, it's not centered, but we've got one resolution element with Spitzer. Now with James Webb, we've got many, many of those resolution elements, so we can do detailed studies. So what we've done, we've started with a couple of those galaxies that are nicely characterized with many, many other data sets, including Centaurus-A, but another one, I'm going to talk about another one here, 326. It's another radio galaxy where now you've got the Spitzer, quite old now, Spitzer spectrum, which was dominated by those pure rotational lines of H2. And you see that the H2 luminosity is really, really high. We've got as much molecular gas as our own Milky Way, 10 to the 9, 1 billion solar masses of warm molecular hydrogen, as much as cold CO in our own galaxy, basically, but with the tiny star formation rate. So very much below what is expected from the Schmidt-Kennickert relation. So this is a very nice, let's say, example of H2 being boosted by mechanical energy driven by feedback. And here we know what is the piston. We know what is the source of large-scale kinetic energy injection. Those are the radio jet of the galaxy. Okay. And so what we did with colleagues at ELPNS, Jorge Villa and Benjamin Godard and Guillaume Pinot-Desforêts, we addressed the question of, okay, what can we do with those H2 lines? Can we extract the relative contribution from the radiation and the mechanical energy in one example like this? And you'll see that the answer is not that obvious. So we built a very simple toy model where we say, okay, within a beam of our observation, we've got surfaces of shocks and PDRs. Okay, and the shocks are actually driven in PDRs. So this is the basic assumption. We pave our beam with those surfaces or with solid angles of shocks and PDRs. And those shocks and PDRs, they can be red shifted or blue shifted if we've got got kinematical information from the lines. Okay, obviously you've got different ways to pave the observational beam. You can have many multiple small solid angles of individual shocks or PDRs, or large one. Here I show the same solid angle between the solid angle of shocks and solid angle of PDRs, omega S and omega P, same total omegas, but different ways to pave the beam. And basically what we say very simply, and I'm not going to enter into much details, but we say that our model emission of or a given line intensity model is a function of the shock velocity and the radiation field. And we say, okay, we separate, we say it's the linear combination of the shock and the PDRs, and those integrations are done over probability distribution functions of different radiation fields and shock velocities. And we explore different shapes of those probability distribution. We explore Gaussian, PDFs, or exponential. I'm going to talk a little bit later on. And from that, once we fit those line emission, we can actually compute the total dissipation rate of mechanical energy, which is given by this formula, because we've got models of shocks, and we can extract, given the probability distribution, we can extract the total kinetic luminosity from shocks, and we can do the same for the UV reprocessed power in PDRs. Okay, we have grids of Meudon PDR models and radiation and shock models from the Paris-Durham shock model. So we explore different range of densities, radiation fields, and shocks. And we basically fit those line emission by fitting those in a log space of intensities. Okay? The aim of that is basically to constrain the probability, the probability distribution function of those solid angles of shocks and PDRs. And here are the quite surprising results. Actually, is that the bottom line is that our best solution. So you see here the distribution is basically a line energy distribution, sorry, the intensity with the different lines we had with Spitzer, but also ground-based raw vibrational emission of H2, and also C+ and O1, and the different contribution, PDRs in orange and green for the shocks. And what you see first is that here you've got the distance between the observation and the models as a function of the density. And you see that the best solution is at low density. So actually, and this is quite very different from what has been inferred from CO observations, for instance, or other gas tracers that were focusing on a very dense material. Here we see that to account for the H2, but also C+ and O1, you need quite diffuse emission, and this is actually in line with what James Webb is now finding in nearby galaxies. You see that the S0 line, the lowest excitation line of H2, and the C+ and O1 are coming mostly from PDRs, as expected, and all the other excited lines of H2 mostly coming from shocks. But now what's nice, I was showing that you can derive the energy budget. Now that you have the best fit, you can derive the total kinetic energy luminosity and the UV luminosity. And the UV luminosity is shown in orange here for all of those models. And the orange bar here is the infrared luminosity of the galaxy. And this is not a fit. This is an output of this fit. Okay, and what we see is that the UV luminosity we need to account for the lines is exactly the infrared luminosity of the galaxy. So the UV reprocessed power is actually coming out in the infrared. So this is a nice self-consistency check. Okay, and what is more interesting, I think, is that the kinetic energy luminosity that you need when you've got the fit of those lines and you've got the numbers here is actually a few percent of the total mechanical energy from the jet, from the radio jet. So this is inferred from radio observations, not entering into the details, but we find that 5 to 6% of the kinetic energy of the jet is actually needed to account for the H2 line emission. So a tiny fraction of the mechanical energy of the jet can actually coming out of H2. And you see here the results for different densities. So as you go up in densities, it's still acceptable for a density of 10 to the 2, not bad. But as you go up in densities, the fit is actually starting to be really bad. And this is a distance index. So 0.5 means that you reproduce all the lines by less than a factor of 2, which is quite good actually, given the number of lines. Okay, yeah. So this, we were there when we actually submitted the paper, but in the meantime, the public observations of James Webb observations of 3C 326 were available. And now you see the spectrum, an impressive spectrum of this galaxy, again, dominated by myriads of H2 lines, but also CO lines. And we say, okay, we take those fits here, and we can predict from our model, we can predict the rest of the H2 lines or even the CO lines from our models and compare to the James Webb observations. And the results are actually fairly good, very good. You see here, so this is not a fit, this is a prediction. Okay? There are quite few predictive models in astrophysics, and I think this is quite a success. The open circles are prediction from our modeling, and the stars are the James Webb observations. The error bars are on the less than the size of the symbol. Okay, it's a few percent for James Webb observations. And again, we find that the mechanical power that is needed to account. So now with James Webb, we've got many, many more lines than before. You've got Q or S lines or O lines of H2. And you see some lines are not well reproduced within 0.5 dex, but overall it is quite good. Okay. There are other evidence from other groups that you only need a tiny fraction of the mechanical energy injected at large scales to coming out from the H2 lines, coming out in H2 lines. Another example is this AGN here in the Stefan's quintet system that was observed with James Webb during the very first early release observations of James Webb, and now what is nice is that we can resolve. So this is the jet orientation, and we see H2 coming out where the jet is interacting with a cloud, with a CO cloud, and you see H2 line popping up where the cloud is. And from the jet distance, the kinematics of the gas, we can actually derive the total energy from the H2 and the jet kinetic energy. And you see that it's also, again, a tiny fraction of the jet kinetic energy that is needed to account for the H2. Okay. So shocks are necessary to explain the excited lines of H2 in those galaxies, but it's only a tiny fraction, and the mechanical energy is reprocessed in mostly the diffuse phase, which is quite of a new result. Okay, let me just show you. I've got 1 minute, maybe 2 minutes. That's fantastic. I was not hoping to show you that, but this is what we had with Spitzer in the Stefan's quintet system, where we detected pure H2 line emission. So we had no kinematical information and very low spatial information. So most of the H2 is located out of this in this intragroup medium outside of those galaxies. And now with James Webb, we've got those images. We see the structure of the gas, and from spectroscopy, we now know that in some of those filters of James Webb, here this is a mirror image that I made, and in green the 10 micron filter, we know from spectroscopy that the 10 micron filter is dominated by the H2 lines. So all of the emission that most of the orange emission that you see here is actually pure molecular hydrogen. Look at the continuum in the center of that region. The continuum, the dust continuum is very low simply because the UV field, it doesn't mean that the dust is not there, but it is not UV heated. It's not illuminated by the UV because you've got a tiny amount of star formation, but you've got very strong H2 lines. And the new, very new results that we've got accepted cycle 3 proposal with spectroscopy, and now we've got the kinematics, and the kinematics looks very quite impressive and very different from CO. This is CO emission at the same scale in the center of the shock. You see that the CO line is 100 kilometers per second wide, centered at the systemic velocity of the galaxy that is falling in that group. And the H2 is spreading a much larger velocity range, 1,000 kilometers per second. So the kinematics and the location of the warm H2 is very different from what we see in CO. So this is a full map of CO. So great things to discover between the different phases of warm and CO, and the fact that H2 is quite a good tracer of mechanical energy dissipation. And here the piston is the galaxy collision. And I'm stopping here with conclusions.